Okay, good morning, everyone. Thank you for being here. And we have the pleasure to introduce Professor Oscar Cavichia, which is visiting us. And he is a product of the University of Sao Paulo. He made his PhD there in 2012. And then he moved for a stay in Madrid, in CMA with Professor Boyar, working in chemical evolution models of galaxies within the study of network, I think. Then he came back to the University of Sao Paulo for a postdoctoral fellowship in 2014, and then he won a professorship in Itajubá, the University of Itajubá in Minas Gerais in Brazil, and where he's still teaching there for a while. And then I know he will move next year to Sao Paulo for 1 year, at least there. And Oscar is an expert, international expert on chemical evolution of galaxies, but also in abundances in general, gradients, as of today, he's going to show us. And in the formation of the bulge of the galaxy, metallicity in general, and all related aspects, all the aspects related to metallicity in galaxies and galaxy formation. So thank you, Oscar, for being here. Yes, whatever you want.
Okay, thank you, Pepe. First of all, to say good morning to you, and thank you for your invitation. Just before to talk about the gradient metallicity in spiral galaxies, I will locate myself in Brazil. So I am now working at the University of Itajubá. Itajubá is a small city in the south of the state of Minas Gerais, which is between São Paulo and Rio. Next to Itajubá, we have the largest telescope based in the Brazilian territory, which is the 1.6 meter telescope. And I did my master and also some part of my PhD with data from this telescope. It's not the largest telescope that Brazil has access, but it's the largest one that's in Brazil territory. So let's move to the chemical abundance gradients in spiral galaxies. We know for more than 40 years that spiral galaxies have abundance gradients in their disks. As I show here, it's an example of metallicity gradient obtained in the Milky Way disk from H2 regions. In general, we see that there is a trend of the abundances in this plot. For the largest distances from the galactic center, the abundances are lower. And the abundance gradients are one of the most important constraints to the chemical evolution models in galaxies. They can be traced using the H2 regions, feed stars, B stars, open clusters, and planetary nebula. Each one of these traces trace the gradient in different H's. And the origin of these gradients relates with the physical process that are acting in these galaxies. So, like for example, the inflow of gas, for disk formation, the star formation history, also the radial gas flows in radial migration of the stars. So usually people do linear fit to this gradient, and we have the slope and the intercept of this linear fit. So for some galaxies, we observe there is a flattening of this gradient for the largest distances in the disk. So this is a paper from Brasil showing that for some few spiral galaxies, there is this flattening of the gradient for the largest distances. More recently, we have the integral field spectroscopy surveys that enable a more comprehensive view of the study of the distribution of metals in the disk of many spiral galaxies. This spectroscopy surveys allows the investigation of many H2 regions in a sizable sample of spiral galaxies, provide the detection of this region and statistical robust results. As I know, many of you were members of the CALIFA collaboration, that observed about 1,000 galaxies in the local universe. The PI was Sebastian Sanchez from this collaboration. And CALIFA was good to study the flattening of the gradients in this spiral galaxy because the field of view of the CALIFA goes beyond 2 effective radius for these galaxies, and the spatial resolution was about 1 kiloparsec at the distance of these galaxies. So this is one of the most comprehensive study from Sanchez-Menguiano in 2016, where we analyzed a sample of 122 galaxies from CALIFA survey, trying to understand the deviation of these gradients in the spiral, the disk of these spiral galaxies. We obtained the chemical abundance for a sample of 82 regions located in the disks of a large sample of spiral galaxies with different masses, using the O3 and 2 index and the calibration proposed by Marino in 2013. When we plotted the gradients of these galaxies, they were scaled here by the mass metallicity relation. And when we plot in this diagram, the oxygen as function of the distance to the galactic center, we see that the main gradients of these galaxies are independent of the morphological type. They are all the same. And also we observe for the largest distance that there is a flattening of the metallicity distribution. Also, the gradient was independent of the bars in these galaxies. So when we plot the metallicity distributions according to the beams in mass for these galaxies, we observe that for the most massive galaxy, there is an inner break in the distribution where the abundances are flatter in the inner parts of these galaxies. So maybe this was related with radial gas motions. So when there was a break in the metallicity distribution, we observed that the main gradient was steeper than in the case where there wasn't a break in the metallicity distribution. And these radial gas flows were related probably with asymmetries in the disks of this galaxy, in the centers of these galaxies. So probably bars or a circunuclear star formation ring could induce these radial gas flows. But however, for 37% of these galaxies, we didn't observe a bar or a circunuclear ring. So we had to explain or suggesting another mechanism of radial movement of gas for these galaxies. Then subsequently, Sanchez-Menguiano in 2018 observed used the data for 102 phase-one spiral galaxies observed with the Muse, and they look individually for the metallicity distribution for all these galaxies, and they proceeded like our previous paper, but using in this case automatic fitting procedure to adjust a linear fit or a fit with one break. Inner break, a fit with one outer break, and a fit with 2 breaks in the metallicity distribution. What was an important result that came from this study was that for the inner break, most of the galaxies show this inner break at 0.5 effective radius, while the outer break, the distribution was much wider, and the peak was in 1.5 effective radius. So the conclusions so far were that galaxies present a similar slope, independent of the environment that they were. There was a lack of correlation between abundance slope and the bare nature of these galaxies. The presence of the inner drop and the outer flattening does have an effect on the negative abundance displayed by spiral galaxies. This can be seen here in this plot, where we see the slope of the main gradient as a function of if there was a break in the abundance metallicity or not. So in the case where there were breaks, the main gradient was steeper than in the case with just a simple linear single slope. So again, radial motions play a fundamental role shaping these luminous profiles in spiral galaxies, producing inner drops or outer flattening in the metallicity distributions. This is also in agreement with our previous paper from 2016. And more recently, Pepe and Igor published this paper showing that there is a difference in the metallicity of the gas and metallicity of the stars in the center of some spiral galaxies. They note that for the most massive galaxies, there is a systematically lower gas phase metallicity compared to the stellar metallicity within the central regions of these galaxies. This difference is not observed in the in other parts of this galaxy. So again, here it's a sign of dilution for radial gas flows or accretion for the circumgalactic medium. So as the nature of this flattening in these breaks in the inner parts of many spiral galaxies wasn't clear, we start a new project that we published this paper at the beginning of the year with as master's students of mine. And we started this project to seek for possible explanations for the inner radial break. The hypotheses were that maybe there was some selection, A2 selection methodology that we are introducing a bias in the metallicity gradients, or maybe there was a contamination of the diffuse ionized gas in the inner parts of this galaxy. So we analyzed for this study 150 galaxies from CALIFA survey. They were all isolated galaxies. The inclination was good to determine the metallicity gradients. They also cover a large interval in effective radius or in stellar mass, and most important, baryon and bare galaxies cover the same range in metallicity, in stellar mass, morphological type, and effective radius. So we use this catalog from Espinosa Ponce to 2020, which published a catalog of spectroscopic information of ionized regions detected for almost all galaxies in the CALIFA survey to calculate the chemical abundance from the A2 regions. So just to remind you that the source of ionization of gas in galaxies can be young OB stars that are associated with star formation regions. In the inner parts of the galaxies, we have the agents that can ionize the gas, but we have other sources of ionizations like diffuse ionized gas, which I will call here just dig. So the dig may be ionized by hot low mass evolver stars, HOMS, shocks, also cosmic rays, and they have different properties than the two regions. Like they have low density, high electron temperatures, low ionization parameters. So if they are classified as A2 regions, they can introduce a bias in the chemical abundance calculations. We follow Lacerda to 2018 to classify the dig in these galaxies. We have the HG, where the ionized regions have H alpha equivalent turbidity lower than 3 angstroms, and they are classified as regions ionized by hot, low mass evolved stars. The MG, which the equivalent turbidity is between 3 and 14 angstroms, the regions are ionized by various mixed sources, and the star formation clumps where the equivalent width are larger than 14 angstroms. These are the star formation complex. So in our sample of about 150 galaxies, we found that the AG component was negligible, less than 3% of the ionized regions. The NG is more important. We cannot discard the NG contamination from our sample. And while most of the ionized regions corresponded to star formation complexes. So the conclusions here that the contribution of a dig is negligible. The fraction of an dig to star formation complex varies along the Hubble sequence in these galaxies, increasing in the later times. And also the later galaxies shows and dig concentrated in the central regions of these galaxies. As the dig proceeds from photons leaking from the H2 regions, then they can reach a mean path of about almost 2 kiloparsecs, and the CALIFA resolution is about 1 kiloparsec for these galaxies. We cannot discard dig contamination from our sample. So we follow a method by Espinosa-Ponce to subtract the dig from these ionization regions. So this method consists in identifying spots that were not classified as H2 regions by the two H2 explorer. Then we calculate the average flux for these spaxels. Now they are referred to as dig. Then subtract this mean flux from the flux of the identified H2 regions. We also consider the standard methods to classify the H2 regions that some are based in the BPT diagram. We use the most methods to select H2 regions, like for example, the Keeling 2001 curve demarcation, which is the one that is outside in the distribution. The Keeling 2001 plus equivalent width cut of 6 angstroms. The equivalent width to the colors shown in the top of this panel, of the first panel. We also use the Kaufman 2003 demarcation line, which is the second one here in the middle, and the Stasiska 2006, which is the left one. We also consider the method proposed by Sanchez in 2014, which is considers the fraction of young starlight that ionize the gas, and it should be higher than 20% to be considered as a H2 region. The fraction of young starlight comes from models of forgot the name.
Underlying stellar population.
Yes, yes, stellar populations. Yeah, thank you. So this one, the color here, corresponds to the fraction of starlight coming from stars or ionized regions larger than 20% in these galaxies. These top panels, we didn't remove the D, and in the middle panels here, we plot the same information, but removing the dig contamination from the ionized regions. So we see that removing dig, the ionized regions, they are spread over the BPT diagram. And so depending on the H2 region method, we can we may have difference in the number of H2 regions. Also, we found that there is thank you. Thank you. Also, we found some difference in the flux of oxygen 3 to 8 beta. The difference is lower than 10% for 70% of our sample. And for the nitrogen 2 H alpha, the difference is lower than 10% for 95% of the sample. The difference for the oxygen 3 H beta were higher in the corners of the diagram, and for nitrogen 2 and H alpha, the difference was larger in the top right and also in the bottom of the diagram. So this can be changed the chemical abundance because we are using the O3 and 2 method. We also consider the one diagram from C.D. Fernandes, which I show here, where it separates in this diagram the star formations from strong, weak, and retired galaxies. Retired galaxies here are ionized by hot low mass evolver stars, and it uses the equivalent width of H alpha and nitrogen 2 over H alpha ratio. This one here is for without removing the dig, and this one here is after remove the dig. So we do see that the number of star formations change depending after dig removing. So the number of classified regions classified as retired galaxies, weak or stronger AGNs decrease after dig the contamination. So in a nutshell, for the Keeley 2001 demarcation curve, we observe a decrease in the number of two regions after dig removing. For the other ones, there is an increase in the number of two regions. And for the Kaufman 2003, approximately the same number of two regions after dig removing. So we proceed to the gradient fitting methodology here. We also implement the automatic fitting procedure to fit the metallicity gradients. We implemented here a piecewise regression where we have breaks in the metallicity gradients detected automatically. We consider a linear fit, a fit with one break and a fit with two breaks. There is a bootstrap here to find the best fit and to avoid to find the global minimum of the fit. And the best fit is based on the archaic information criterion in this case. Then I show you here the results, the fit gradients with dig in this case. We see that depends on the two region selection criterion, the fit changes. So for most of them, there was, for this galaxy, there was a break detected, but for the method of Sanchez 14, we didn't find a break. So this method basically removed two regions or ionized regions that are located in the inner parts of the galaxies. So because of this, we can't find a break. So this characteristic we found for most of the galaxies that we analyzed in the sample. And after we subtract the dig and also study the effects on the metallicity gradients here. So we see that for some galaxies, after removing dig, we didn't find a break that was before. And for someone, after removing the dig, there was a break detected in the metallicity in the inner parts of the galaxy. In summary, 25% of our galaxy had a break, inner break in the metallicity gradient before subtracting dig, and 22 after subtracting dig. We also found that Kaufman 2003 demarcation curve is less affected by the diffuse ionized gas, and the Sanchez 14 selection method removed the largest number of two regions in the inner parts of the galaxies. So from now on, we adopt the following procedure. We proceed as the contamination of the dig from our ionized regions and consider an inner break when in at least 3 ATU region selection criteria we detect this break. And I will show you some correlations that we found. First, the influence of the galactic bears. So we analyze the position where the inner breaks occur, which we call it here H1. And we see that there is a correlation with the presence of the bar. For bare galaxies, this position is located at large distance from the galactic center, while we didn't find any correlation with the slope of the inner break and also the slope of the main presence according to the presence or not of a bar. We also found some correlations here with the position of the inner break and the stellar metallicity of these galaxies. For the most massive galaxies, the inner break occurs at near the center of these galaxies, while the slope of the gradient is larger for the most massive galaxies. So more massive galaxies have remarkable inner breaks. They are steeper and closer to the center. We also found some moderate correlation here for the mass of the bulge and the effective radius of the bulge, but the most important result was this correlation with the stellar mass. Now I will move to recent results that we are obtaining in the Milky Way galaxy with planetary nebula. It seems different, but in the end, you will see that the results are related with what we are doing with other spiral galaxies. So we can also probe the metallicity gradients using the planetary nebula in the Milky Way, and also in other galaxies, of course. Planetary nebula are older than H2 regions, of course, so we can probe the gradients about 2 to 4 gigayears ago. And what we see from planetary nebula is that the gradient, the metallicity gradient is more scattered than H2 regions. So maybe this is related with the uncertainties in the chemical abundance from these objects, or the uncertainties in the distances. As probably you know, planetary nebula distances are very uncertain, or they were, because we don't have a physical parameter like stars to derive directly the distance. So we have to use statistical distance scales to derive distance for these objects. And we started a project to derive better distance for this sample of planetary nebula. We performed a recalibration of the H-alpha surface brightness relation, radius relation, using Gaia DR3 data. I will show here example. So we matched a large sample of planetary nebula with Gaia catalog to obtain the parallaxes for a large sample of this planetary nebula. And for the best parallaxes with uncertainty lower than 15%, we calibrated this relation between the surface brightness in H alpha and the intrinsic radius of the planetary nebula. So the intrinsic radius, with the intrinsic radius, we can obtain distance for planetary nebula that we can obtain Gaia parallaxes with good precision. So this is a statistical scale, right? This calibration yields distances that are on average 30% lower than the previous calibrations in the literature. For those planetary nebula that we had Gaia parallaxes, we proceed using a Bayesian approach, using the statistical distance as priors, and also the parallaxes to derive the distance. So I show here some posteriors that we have, but we could calculate distance for about 400 planetary nebula with this method. Then I show here the distribution of the planetary nebula in the galactic plane, as seen from the North Galactic Pole. We had some, at the projector here, we cannot see, but we had some planetary nebula that were located near the spiral arms of the galaxy. Also, we detect some planetary nebula in the bulge of the galaxy. The color here is the extinction obtained from the Balmer decrement. And I derived the metallicity gradients for a sample of 230 planetary nebula, this planetary nebula. As you can see here, we used here distance providing from the Bayesian method, but for those planetary nebula that I didn't have the parallaxes, I used the statistical distance in this case. The oxygen abundances here are from the direct method. And we also consider breaks in the metallicity distribution. So we consider the same procedure as we did for the CALIFA galaxies. We also did it here. And we considered the case with one break and two breaks in the metallicity distribution. And the one break was located at 7.8 kiloparsecs. The two breaks, the one is located at 8.3 and the other one almost 10 kiloparsecs. The computed likelihoods of all the models didn't allow us to choose these piecewise regressions as the best fit. So we have to stay with the simplest model, which is in the linear fit with a single slope. But there is evidence that the gradient is changing the slope in the Milky Way galaxy for planetary nebula. After, as we have many objects located in the galactic disk, we derive a metallicity map using a Krag interpolation to model the spatial relationships between the points, and also a Monte Carlo procedure to take into account the errors in the distance and also in the chemical abundance. So as you see here, this is the position of the sun. We observe the enhancement in the metallicity near the sun position, and it proceeds towards the end of the galactic bar, this enhancement. The enhancement of the abundance is not so high, but they are in the order of the errors, observe the errors. Also, we observed here there is a transition in the abundances near the sun, where it seems that the galaxy had a bimodal chemical evolution. One is in the inner galaxy and another different in the outer galaxy. This change of slope in the detected in the piecewise fits and also in the metallicity map, they do agree with the Milky Way rotation radius, which is about 8.5 kiloparsecs, located at 8.5. So maybe in this plot here, we are seeing the effects, the dynamical effects of the rotation radius in the metallicity distribution. Well, I'm using the PDF, but maybe you can see some results here. We also, as we had proper motions from Gaia and the radial velocity for many planetary nebula in our sample, we separate them in thin, thick, and disk in halo. Then I calculated the gradients, separating all the planetary nebula that we could had Gaia proper motions with those with thin disk planetary nebula and thick disk planetary nebula. And we observed that for the thin disk, the gradient is more steeper than for the case for the thick disk. So probably we are separating the planetary nebula in age here. These are the oldest one, and these are the youngest one, which still have the information of the gradients in the galaxy. So this gradient agrees is in good agreement with the gradient obtained from H2 regions, the recent gradients from H2 regions. So it seems that in the last 2 gigayears, there is a memory of the gradient in the galaxy, and it's not erased by the chemical evolution and also migration of the stars. So I came to my conclusions here. First, for other spiral galaxies, we observed that inner breaks in the metallicity radial gradients seems to be related with radial gas flows in the disk of these galaxies. We also find that we don't need galactic bars to produce these inner breaks, but when there is a bar, the gradient is amplified. The inner break is amplified. More massive galaxies have remarkable breaks. They are steeper and closer to the center. And the diffusionized gas affects the inner breaks. The Kaufman demarcation line is the best one, the less affected by the diffusionized gas. For the Milky Way, we see that the break is obtained for planetary nebula is located near the solar position. And also there is a memory for the structure of the gradient today. And since that the galaxy retains a memory of how it evolved chemically and dynamically over the past 2 gigayears. So thank you very much, and I'm happy to take questions.
Thank you, Oscar, for the very interesting talk and results. So we have time for some questions. Raúl?
Hello. Very nice talk. I wanted to ask about the sample used in this paper. I understand that it's basically all the CALIFA sample independently of what kind of galaxies are you including in the BPTs and the analysis, etc. You're including AGNs in the sample. Are you looking for a specific inclination of the galaxies, so everything is mixed in the same analysis?
Okay, we didn't look specifically for AGNs. We have some galaxies with AGNs in the sample, yes, but we didn't look specifically for an influence of the AGN just in the BPT diagram to separate the ionized regions. But of course, it's an important procedure to go, and I think that maybe there is some influence. As Pep told me that there's a student working with this, and maybe it's better to ask you to Borja about this. But okay.
Yeah. So I understand that you don't make the separation of the distinction of the dig and H2 region, because that was already done in the paper that you said, no, of 2020, that used the catalog of H2 regions, and you use the already done catalog, no? Or
Yes,
H2
but it's not separated. H2 regions from IGNs. We did the separation later. There they just give the fluxes for the ionized regions detect, but not separated yet.
So no separation.
No,
It's a sub.
yes, before, but
Can you talk a bit more about the method that you use to identify the breaks in your profile? Because in some cases, they don't seem very obvious to me.
Yeah, related to
This one?
question.
Yeah, this one.
In some cases, you only have 2 points.
yes,
That drives the break. So I was gonna ask that.
yes. Well, the method it's based on a bootstrap where we remove the points and you perform the straight line fits. So it's based on, maybe I can show here. So we calculate for each one of the fits the 3 possibilities to fit the gradients, and the best fit is obtained when we calculate the archaic information criterion. So it's related with, it takes into account the complexity of the fit, if you have more free parameters, for example, and also it takes into account the number of points, because when we have a lot number of H2 regions, we have to introduce a correction to calculate this archaic information, the IEC, right? Then we perform this bootstrap and take the best model as the minimum IEC. So the AEC, the scatter of the distributions are considering the fits. So in this case, you clearly see there is a break, but some case the break is not so visible. Like, for example, you have a scatter in the first, the white panel in the top. But this is the method that we adopted. So we thought that it was the best available so far.
So do you allow for some margin of error? For example, if I look at
Yes, we did.
white panel, one might argue based on some of the cases that are there, for example, that you could identify more than, at least 1 or 2 breaks there. Bottom right, for example.
Which one?
Bottom right?
Yes.
Yeah, that one, for example.
This one.
So,
Yes, this one is interesting as your point, because depending on the A2 region selection method, we remove A2 regions that are located near the center of the galaxy. So sometimes there was a break here, but in this case, we removed the regions that were located inside, and we couldn't detect the break after. Just because of the criterion. Okay.
Diana?
Yes, very nice talk. Thank you, really. I think coming back here, my comments were related with AGN as well. If you did any deeper study, because I think it would be really interesting. And actually, here you can see that when you are using like the bottom, the three plots that are at the bottom, when you use the three different methods for selecting, so in QLib, that is the line from 2001, that's like the last line. So there you are getting a much stronger mixture with AGN, because you included the H2, but you also include many composite galaxies that have both star formation AGN. And then in the second, that is Kaufman, you still include also some part of composite galaxies, so you can still have some AGN. Well, when you come to Stasiska, it's much more strict with selecting star-forming galaxies. And you can see that, I mean, that break, although you have a small number of sources, you actually select that break in the first two criteria, but not in the last one, you know? So, I mean, the statistics are not the best in terms of the points, but it would be really interesting that you can do a bit in order to understand the origin of the break. To really, I would also suggest that instead of QLI01, you use QLI 2006, that is a bit updated version with better, it's a better separation. So I think it would be really interesting. Also, another thing, I don't know if you checked, for example, the infrared data and X-ray data to see if you also have some of the obscured AGN that might not be in your plot where you separate, you know, I mean, when you are checking a bit the photoionization between star forming and AGN composite, but you can also see if some of those that you are having might be obscured AGN as well, either Compton tin or Compton thick, you know. So you could at least check with WISE, and if there are far infrared and infrared data, then even better. And I suppose that X-ray data are also there for some of the sources.
Thank you very much for your comment.
Anyway, I really enjoyed the talk. Thank you.
Thank you.
Yes, you talked about the presence or not of bar, but have you looked at the strength of the bar?
The strength, yes. We looked, but we couldn't find any relation with the strength of the bar. So we didn't publish this.
I have another, I don't know if yes. So I think at some point you mentioned that these are all like isolated galaxies.
Yes.
Yeah.
So how they were really defined? So when you say isolated, it means they are like not in groups, clusters.
Yes.
Pairs. Okay.
Yes. We used the classification from the CALIFA sample for they provided this classification, so we didn't look individually for the images.
I have more of a curiosity than a
Yes,
question.
yeah. So,
Regarding the AV distribution that you showed in the galactic plane, that you have the planetary.
For the Milky Way.
Yes. No,
Okay.
Yes, this one. So you saw the planetary nebula as a function of the AV, right? The values. So my curiosity is that if you find any relation between the AV and the location of where it is in the galactic plane, like whether in the arms or in the center, in the outskirts, if the AV changes in some particular way, depending on where it is
Yes, there is some relation. I didn't look in detail for this, but for example, planetary nebula located near the bulge or bar, you'll have a larger extinction for these objects. So in near the solar position, the extinction was much lower. So we do have seen, yes, a correlation between the positions and the
Yeah, so
extinction.
then it could be interesting to see like the values of the AB, but also like as a link to the stellar populations or so on. The
Yes,
ages
yes,
and
it's something that I can do in the future. Thank you.
So now I have a question. So that's very interesting that actually, I mean, the number of breaks in the gradient is even more difficult than whether there is a gradient, which is already
Yes.
a big question for galaxies that is in debating now. But so let's say that there are some peculiarities in the definition of the number of breaks, because you have shown that even the subtraction of the dig is an important bit of information. I think that's very important because even myself and many others, we haven't taken in the past into account the AG, in particular in the inner parts. But in your opinion, after having done this work and so on, so the dig influence for the gradient definition depends on the methodology you use for the gradient definition. So in your opinion, what are the lines which are to be avoided and which are the emission lines which are more robust? So which are the indicators which are more...
Yes, I didn't look specifically for the emission lines to calculate the abundance, for example, but let's wait.
Sure.
What we see and in this study and from other studies from Laura Sanchez Mingano, for example, is that the number of galaxies presenting a break varies depending on the methodology to calculate the abundance. So, for example, if you use the O3 and 2 or N2 indexes, change the number of the galaxies. So, but so far, as we did in this work and in the other works, everyone is using O3 and 2. But there is a consequence for that.
I mean,
Yes.
it's honest to show all the possibilities and how
Yes,
they affect.
that is, it affects the chemical abundance because we do see the ratio changing depending on what you are using. So you have the O3 and beta changing less than 10% for this case, and nitrogen 2 and H alpha changing. So it's important, and we do expect a difference in abundance, for example.
Yeah, I suppose that in the inner part, the lower ionization stages are more common, maybe. So low excitation lines are more common, sulfur 2, nitrogen 2, these kind of things. So that will be more affected probably by the subtraction of the DAG for the inner H2 regions, which are very interesting. I mean, you mentioned the work we did with the Igor in the past, 2 years ago. So it's a very interesting possibility whether in the inner central part, let's say between 0 and 3 kilobars from the sun, where there are any kind of change in the gradient that you have shown that there are gradients, and they're very, very intense break. And this is important maybe when we are trying to investigate, and Miriana said actually the origin of the breaks, which are happening.
Yes.
You didn't enter into that because I think it's another talk or something like that. But maybe even the feedback from the AGN or the bar, or whether the bar is young or older or strong, that kind of things have to be. But I think it's a very important work that has to be done. Whether are we able to derive with precision in the inner part of the center of spirals there is a break or not, or that I think is very important. So you think we are more or less with your paper in a good stage to confirm that I think you mentioned 32% of the
Yes.
big galaxy has this inner break in the graph.
30%, yes. Almost 30% of the galaxy have.
Of the CALIFA.
Yes. But it's interesting because all these galaxies are isolated, so you
Yeah.
don't know
Yeah, this
what happens
the
with
mystery.
interactions too.
Yeah.
Maybe interactions may produce this break.
There have been papers from Brian Tapia, for instance,
Yes.
the last one I remember with the group of Tisera Patricia in Chile. With interactions and other before, with interactions you can produce breaks in the gradient.
Yes.
That's well known. But without the possibility of a nearby companion, it's even more complicated to explain why it would be more complicated to explain why the shape would change. So
Yes.
maybe you have to think on the kind of feedback or other structural co-rotation or something. But I
Yes.
don't
What that would be that in the case of these galaxies, the secular evolution is actually taking the role in metallicity gradients basically instead of any interaction. So I think really yes, I would say the AGN feedback and testing that would be the first thing to do. It's because it's also after the star formation feedback the next strongest indicator.
Other more exotic possibilities are this
Yes.
kind of dwarf galaxies falling into the center.
The center,
I remember even with Barr, there were many years in the 90s and 2000s looking for the possibilities of a correlation between the shape of the gradients flat or not, the slope and the presence of a bar. And after so many works, the conclusion was we don't know. Still, I don't know. That would be maybe because the definition of the gradients themselves was difficult because of these kind of things.
Yes.
You have to take, you have to be very, very detailed in the way you subtract the influence of the diffuse medium, and that was not done in the past because they were not 2D devices. They were just multi-oil spectroscopy or slits. Well, if there are no more questions.
I have a question. I'm not sure if I understood well, because you saw the analysis when you take in account the decontamination or when you remove the decontamination from the catalog of 2020.
Yes.
But you also make this difference that may Lacerda about the kind of the type of dig depending on the equivalent width of H alpha. That means that you don't consider any region with equivalent width higher than any value of equivalent width. I mean,
No.
you put a limit in the equivalent width of H
Yes.
alpha when you consider which is dig and what is not dig.
No. What we did was for some region selection method, we consider the equivalent width of H alpha. But to subtract the dig, not. To subtract the dig, we just had the H2 regions selected by the PyH2 Explorer. And what was defined as dig was the spaxels that were outside the region. So you calculate the mean flux for these spaxels and then subtract from spaxels where there are detection of H2 regions. So for this method, there is not information about the width of each alpha.
So maybe you found the region with equivalent width of 3.
Yes, we
maybe
don't know.
with equivalent 3.
Yes.
Okay.
Yes.
Okay.
But later, the equivalent width is considered for some selection methods.
Okay.
There is no question.
No.
Okay. So there is no more question. Thank you, Oscar, for. Vamos a alguna cosita.
Sí.
Un momento. Digamos,